Hi, everyone. Good afternoon. Thank you for joining our session here. My name is Javed Roshan. I work as Director of Data Services at Capital One. I'll be joined by my colleague Mukram Aziz here shortly. We are here to share with you our experiences in building a data platform for reporting. The storyline for today, I'll go through the use case, the new data platform, and our choice of technology, design decisions behind them. We'll share with you our solution stack, and then wrap up with some of the challenges that we are addressing. So data and data analysis to drive a business strategy is the founding principle on which Capital One has been built. We are one of the first financial institutions to have created the product strategy based on analysis of the data back in late 80s, early 90s. Fast data and its relevance in operational reporting is the use case we are solving. By fast data and operational reporting, what I mean is driving intraday business decisions, monitoring process quality. An example is the time takes for our staff to approve a loan application end to end, right? That's one of the ways of monitoring the process quality. So where do we get the data? We have operational support systems as a source of the data. We have business support systems. And then we generate a lot of data internally by our marketing, sales, and servicing teams. And also, we have third party from where we get the data. So for this use case, a simplistic view of the landscape is we have these multiple data sources that I just mentioned. And then we perform traditional batch ETL processing on this data, right? And we store all of this data into multiple data destinations, predominantly RDBMS kind of databases as well. And then we run a slew of reporting tools on top. So there are obvious opportunity areas given this current landscape, and we wanted to turn our operational reports into near real time and meet high availability SLAs with 4 nines, rapid time to market delivery, as well as reduce the cost of developing new features or enhancements. So the data sources would remain the same, in the new or the existing stack, right? Reporting, we kind of streamlined from various different processes that we had to the new platform. So the 3 key components we changed. We have to transfer the data and also make it available for distribution to various other systems. So we choose Kafka for this. And the data transformation that is needed on the reports, they are written in Go and Dockerized and deployed in Dockerized containers. And all of the raw as well as the transformed data, we stored in one single data destination, which is Cassandra. And then we decided to time bond the data that we are storing on Cassandra to 2 years. So, and then all of the solution, we decided to deploy it on AWS in the cloud. The 2 key driver decisions to get away from the batch processing on the new technology, on the new platform, is move the data when it is available, and then process the data either partially or completely whenever that last data element arrives, right? I'm going to talk about why Cassandra, and then I'm going to hand over to Mukram to talk about the solution stack. So what are some of the design decisions that we have to go through? Let's dig into Cassandra. As you all know, Cassandra is an AP system, right? Availability and partition tolerance is what it provides. And we have to work to tune the consistency. And given that as a feature from Cassandra, that was the right fit for our use case. We wanted to get away from the joins, which are costly in RDBMS. So the combination of partitions, denormalization, and the wide row tables was a no-brainer for us to adopt. We wanted to build our new data platform incrementally rather than a big bang cutover. So Cassandra's linear scalability was important for us. As and when we get more data on board into the platform, we wanted the system to scale as well. Last but not the least, out-of-the-box multi-data center deployment was an obvious choice for us. I'm sure you all know writes are fast in Cassandra. You have to model the data for the reads. Since we are incrementally building the data platform, we constantly looked at the read patterns we know at the time to decide how we should store the data. Partition keys and size, I'm sure we have heard this many a times here in this conference here. This is where we had the push and pull within the teams to decide what should we optimize on. Certain partition keys help us satisfy a good number of query patterns, but then you also have to consider the size of the partition so we don't skew the partitions too much by having big partition storing on one node of a cluster. So let me give you an example of what we did as a data set that we want to model. Car loan applications is one of these cases that we had to handle as part of our financial services organization in Capital One. We consider time series. Do we want to store the data as the time series data? But then soon realize that there are going to be these loan applications that we might get from various dealerships that might skew the size of the partition hugely in a day. So we decided that we're not going to go with time series. And for this specific use case, we decided to use an application ID as the partition key. And an application ID has good amount of data size-wise. And then the partitions are going to be many number of partitions spread across our cluster. So we decided to stay around 50 to 100 MB as a partition size. There are a number of questions we go through while modeling data. Some of them are, how do we do consistency? Is the reading and writing by quorum, is that good enough? Right? If you want to use DSC search, you'll have to think about the same thing. Do you want to read the data? If you read the data using DSC, then you have to think about how you're going to write the same data and what consistency you're going to use to write the data. So a bunch of options available through indexes. There's a cost of using each of these index types to query data. Data is modeled to address specific read patterns. Once you model the data, you might not be able to fit another query pattern into it. So, and that is rightly so. So the rub is going to be making a decision whether you want to come up with this different data model strategy to satisfy this one or two extra read patterns you want to fit into your data model. So DSC search provides many options to query data, like range queries, regular expression-based searches, non-equality based search, group by, etc. These features are very tempting to use. Again, the question is going to be, do you want to use this approach to query the data? And if you are, and you're querying the data, do you guarantee that each time you query the data, you're going to get the same results back? So all of these questions. So how do we address these questions? This is the slide or the table that we have spent most of our time to decide how do you want to model our data. And I've heard some of these questions asked in the previous session. What is the silver bullet? And how do you know which data model is right for you? I would like to point out the consistency formula that is out there. I'm sure most of you should know. But let me know, have anyone seen this or know about this consistency formula? Good. So let me briefly explain with an example. So data stored, let's say, with a replication factor of 3, right? The sum of the read and the write consistency should be at least 4 for you to get the consistent data back, right? So quorum, in this case, for a 3 replication factor will be 2. So if you're reading by 2 and writing by 2, these are 4. So you're guaranteed that if you do that, then you're going to get consistent data back. So that was one of the key things that we would have written on a board that we'll always go back to. And then we look at what are the different data access options we have that we want to model our data against, right? So the table, if you look at it, the first couple of rows go in pair. The second, the third and the fourth rows goes in another pair. And then you have DSC search in the bottom. So we have assessed the data model based on the various aspects of the data that we store. So let's take at the row 1. You can't get away with it, right? Because this is the basic data store option that you have to come up with, right? So the colors, the beige colors that you see on the table is basically highlights what are the pain points that you're going to feel if you're going to go with that. So if you model the data, you partition the data, you're storing the data, the thing is that there are limited features with which you can search that data. So let's say there are a bunch of columns you decided to be your partition and clustering keys, right? So you can only search based on those columns. Now, if you have another column that you want to look at to see if you can I search with that extra column, you will not be able to. So now you have to think about options of how do you want to optimize your data store, right? The next row in there, that you can duplicate the data, right? Duplicate the data with another partitioning scheme so you can fulfill the search criteria of how you want to read the data. But then you'll pay a price for that. What is the price? Your storage is going to go up because you are duplicating the data. You're storing the data again. Depending on what replication factor, you have to consider that as well. And then, as an application, you have to maintain the data. So you are storing two different data sets in two different tables, the same data. So from an application perspective, you have to maintain that consistency across those two stores. What other options do we have? Well, inverted indexes and secondary indexes. Probably there's a trade-off. Well, inverted index, again, is another option where, as an application, you are creating the data as an index, and you're not necessarily duplicating the entire data, right? So that's another option. Again, the penalty that you would pay as an application, you have to manage that. Secondary indexes is an option. I think I've heard people ask you not to adopt it, stay away from it, because the way it behaves is different than how a regular partition would behave. But there may be a use case in your situation that you might find it useful, right? So you have to look at the cardinality of the data that you're trying to index on. And if that cardinality is small or low, then you can go with it, because the way the second indexes work is you do get the parallelism with which you can query the data. And finally, DSC search. DSC search is very versatile in nature. We have looked at the option in the previous slide. But it is slower relatively to all the other options. The consistency is one other thing that you have to keep in mind, because you're always going to read by one consistency, which means going back to the formula up there, you'll have to have the right consistency for the same data that you want to read through Solr. You have to do it by replication factor. So we have benchmarked it on a subset of data. We took about 22 million rows of data on a 6-node Cassandra cluster. You can hardly see the numbers here for the primary and the inverted indexes. Secondary indexes, came third, and the Solr. So some of the performance tuning parameters, we looked at for our specific use case. We used 3 replication factor for the use case that we have addressed. We are a write-heavy database. So we have increased our concurrency writes to 64, and we decreased our concurrent reads appropriately to 16. And we adopted the more stable size tier compaction strategy. Cassandra cluster with DSC search enabled on all of them. And I think the recommendation is that if you go with that, virtual nodes don't even enable it. I think default is 256. We felt that 16 optimization is worked well for us. All caches we disable except for filter cache. And since we have deployed this in cloud, we used EC2 snitch. This is the way the rack awareness Cassandra has implemented. We use 3 availability zones and using EC2 snitch, so our replication factor 3 worked perfectly well for us. And DSC search software auto commit, we actually bumped the time to 10, and we hardly use that. With this, I'm going to ask Mukram Aziz to come over and talk about solution stack.
Sure. Hey guys, I'm Mukarram Aziz. I'm helping build Capital One, a new data platform, a new, modern, near real-time, distributed data platform for operational reporting. Did I get that right, Javed? Okay. So you've already know that Cassandra is our final data store. We did a lot of good work in actually making it happen for us. It is working out for us. But there were other components also that we had to build when we were trying to build this new data platform. So I'm going to talk about a little bit about the ecosystem that we've built and the different technology choices that we have made. So before I go into a lot of details and explain the slides, I'd like to point out two things as a baseline. So what we did was we actually had, I would say, an independence to build this platform from ground up. So we have a wonderful leadership team in Capital One, and we were asked to build it from ground up. We did not have to leverage any existing technology. We did not have to leverage any existing infrastructure that was already built in Capital One. So we had that freedom. So we had that, we looked at it in a way where we were starting this platform from ground up. And second thing that we knew very early when we were designing it, that we're going to deploy this in the cloud. AWS, like Javed mentioned, has already been our chosen cloud platform. And we knew that the services that we're going to deploy, the software that we're going to build, all would have to be run in the cloud. So that gave us two distinct challenges and advantages at the same time. Distributedness of the cloud, we'll have to build software that is actually distributed. We'd have to choose technology that is distributed, because cloud can now give you that freedom to actually build a distributed system. And also, we had to build resilient systems. With the cloud, we knew that things would go down, your nodes would come down, your networks break down. So we'd have to build a fault tolerance, a resilient system that would stand up any breakdowns in the network. So coming back to the slide, when we started to build this platform at the very outset, based on the particular use case that we had, we knew that we had to solve for two problems. We had to build for two different areas. One was we were pulling a lot of data from a lot of source systems. So we had to build for data ingestion. And then we actually would also have to build for data transformation or data processing. So data ingestion, because we had a lot of different sources or data sources in Capital One. We deal with Oracle databases. We have SQL servers, mainframes. We had manual files, Excel sheets. So we had to pull this data from all these different source systems. And while we do that, we also would have to process it while it comes into the platform. So data, when we actually had the data in rest or in motion, we would actually transform the data, aggregate it, process it, do some monthly rollups. And that's where we also had to solve for the data transformation part. So what we came up with was a single stack of a framework. We looked at Spark, we looked at Samza, we looked at Kinesis. We also looked at Storm, because the use cases for those particular technologies were similar to what we are trying to build. But eventually, we decided that we'll stand up our own data platform. It is basically written in Go. How many have you written any code in Go in here? Okay. So we are a big fan of Go in Capital One. We actually are very pleased with the extremely fast build times and run times it gives us. It also brings an overall agility to the development team, and we are happy with it. Most of the platforms, most of the services that we are building, at least for this particular use case, is being done in Go. So the core of this framework is basically that you have plugins. You have developers who write the plugins that are basically run through a runner. All this is basically run as a single service. And then you would have an input channel and output channel in which data is coming to the plugin, and basically the data is getting processed, and then finally it's being sent out to the output plugin, which is actually a reference to the next plugin. To create a service, we have to chain these plugins together and bootstrap it with a configuration file. This configuration file has details on what the parameters that the plugin would need, which order the plugin needs to run, and how the microservice will actually behave in the end. An example of a service that we would write typically would be, we would write something where we pull lots of data from an Oracle database, process it as it goes into our service by setting up a lot of different plugins in that order, and then finally outputting that processed data into a Kafka topic. So because we had to reuse a lot of plugins, we wrote a lot of common plugins that would help the entire development team. And by the way, we have plans to open source this in near future. It would be available in our open source community. So we had to write plugins. So a typical plugin would be an Oracle plugin, a SQL Server plugin, a Kafka plugin, in which you would be able to at least read data and finally even write the data too. A call out to Docker here, once we had that plugin framework that we have built, now we had to look at how to deploy that code. So as you can see, we actually run all our services in Docker containers. So all our services and most of our infrastructure items or infrastructure components that we build are actually running in Docker containers. Most of our DevOps happen in Docker containers. The message within the team is very clear. Any code that you're going to write, any service that you're going to deploy, any infrastructure item that you're going to actually use would have to run in a Docker container. And all our builds, all our services, all our tools, they're all Dockerized, and they can actually be run in any framework or any infrastructure wherein we would have a Docker runtime available for us. So once we decided with the deployment model, the framework, we had to find a way where we would actually have message distribution. So we would have multiple different components, processes that are actually playing around in this platform. And we needed to find a solution so that we can pass messages between these different components. So huge amounts of data had to be moved between two processing units. Kafka was our choice. We looked at other technologies out there, other open source technologies. And we decided on Kafka because it gives us very high availability as well as high throughput. So Kafka serves three purposes for us. It acts as a buffer. So we have two different components that are actually processing at a different rate. So instead of creating a back pressure, we use Kafka to actually act as a buffer between these two components. We also use Kafka for distribution of our messages or distribution of our data. So while we get this huge amount of data into our platform from multiple data sources, there are other clients who are actually also interested in that data. They could actually, because the data in rest is going to be in Cassandra, we would not want to expose Cassandra as a distribution channel for our data. So instead, we would make this data available through Kafka to other external clients within Capital One who are not local to this platform. The third part that Kafka serves is that it helps us to do the replay mechanism. Things go wrong. We've ingested a lot of data. It resides in Cassandra. We would like to make a bug fix. So instead of pulling in the data again from the data source, we actually just replay it from the Kafka topic, and the data is available to us. So once we have the Kafka in place, we had to think about other components as well. We looked at an API server. We had to create an API server from scratch. Again, it was built in Go. We created a mini framework all the way in native Go, which would help us to stand up an API server or a web server in no time, and it uses an MVC architecture. We also needed a mechanism for service discovery. So we looked at Zookeeper, we looked at etcd, we even tried Redis, but we decided to use Consul, mainly because it is distributed and it is highly available. So Consul was our choice because all our services, when they start up, they actually have to be bootstrapped. So a service, when it comes up, it has to be, it goes to Consul, discovers who it is, and then also discovers other services that it needs to talk to in that platform. So once we have the components ready, we looked at where we're going to deploy it. So AWS is the obvious choice that we have made, but then we knew we were going to start a lot of EC2 instances, and we had to basically start a lot of Docker containers when we are going to deploy this platform and our services. So we decided to basically look at Mesosphere, Mesos, to help us manage all this cluster information and do the cluster management for us. So Mesos abstracts the entire data center as a single machine and allows us to launch large amount of containers at scale. It also provides us a consolidated view that our DevOps team can actually look as to what's happening in the entire data center and look at the server resources like disk usage for the entire data center, memory usage, and also CPU. And then finally, we use Marathon to actually run our services or containers. So Marathon comes with Mesosphere, and we use it for our deployment model. Marathon helps us to starting, deploying, scaling, stopping, managing our Docker containers that are highly available services. So again, our stack, basically it looks like this. This is our new data platform. We have Cassandra as our data storage. We are using our in-house 100% developed a Go-based plugin framework for all our data ingestion and our data transformation. We use Docker for packaging and deployment. We have Mesosphere and Marathon for our cluster and our instance management. And we use Kafka for data transfer and data ingestion and distribution channel. We use Consul for service discovery and configuration management. And finally, we use Jenkins for continuous integration. So a couple of benchmarking slides that we had was, we actually tested for a functional group. We had a 6-node cluster, Cassandra cluster, a 6-node Kafka cluster. We looked at pulling 1 year's worth of data that ideally we would pull in production in a day. So it took us about 6 hours to pull this data. We processed about 450 million rows from Oracle and transformed them, denormalized them through our data platform into Cassandra, and it amounted to 11.8 million rows in Cassandra. The rate of processing for the Go platform, just the rate of processing, how we were processing the messages, was around 300,000 messages, transactions per second. And from an overall basis, from a platform perspective, we were actually handling about 21,000 messages per second with this platform. And as you see, most of the time that we spent was getting the data into the platform, but once it came in, it was a smooth ride and it was processing at a very high rate. So with that, that's my data processing engine, and back to Javed.
Thank you, Makram. Okay, a few challenges just want to call out. I think some of this we have discussed. Not all query patterns were known. That's a challenge that we have addressed. Index rebuilds are costly in Cassandra. We all know about that. Deal with it. We are moving from a real-time to a batch to a near real-time platform. So we had to always go back to our business, talk to them. Whenever we talk about any of the metrics calculations, the way they still think is more batched. So that's a challenge that the business are going through to adjust. The entire stack that we're looking at is new. So our operational staff, great guys to work with, they are adjusting to that. Backup restore is, I think it's one of the questions that is very common in Cassandra. You take a snapshot, which is your inconsistent snapshot, which is taken at a node level. Can you take a consistent snapshot of it? We're working with our team at Datos to work on that. You know, we are doing a POC with them. And thank you guys for all your great help. And you know, finding talent is another challenge. You know, we are hiring, so come talk to us. You know, visit our Capital One website. You know, we are hiring across the nation. You know, where there are multiple locations. I think that's all we have for you. Thank you, and we are open for any questions. Yes, sir.
Why did you choose to develop it versus Spark Streaming? I know you mentioned that you evaluated Spark Streaming and Samza and other frameworks. What led you to choose to develop from ground up?
Yeah, so there is an ingestion framework that we had to write no matter what. So we went with a specific framework for that. Then we realized that, you know, do we want to really go with another framework, Spark, or any other complex event processing engine? Do you want to use that, or can we just leverage what we have built? Because what we really see is a replica of the same ingestion framework is we can completely leverage to do our transformations as well. So we didn't really find a need in our use case to go set up another set of layer And we are pretty much leveraging whatever we have developed here. There are different discussions that we have heard in this summit as well, that there is localization of processing that Spark can help when you really process the data across your cluster. We might look into Spark, but for the case that we are in right now, we didn't really find that to be useful, and we didn't want to really add more infrastructure or frameworks on top of what we already have.
So you guys had a slide up there which talked about the different types of indexing and data modeling schemes. Have you guys given any thought to materialized views, and what are your thoughts about it?
Yep.
Using materialized views on Cassandra.
Yeah, so we actually are using 2.1 version of Cassandra, and we believe that materialized views are going to come in the next version, the 3.0. So we are waiting for that. Once it comes, we'll definitely take a look at it. We are interested. Well, while we were actually looking at it yesterday, we were talking about how we could actually relate to that and basically look into it into more detail. Definitely, we're going to look at materialized views.
Given your stack, how did you stay agile during development with regards to the Kafka topics, relaying the topics to the different consumers, and then migrating your Cassandra schema? Did you coordinate any of that, or how did you document that?
So let me repeat the question. So you're asking about Kafka topics. How did we set it up to help us with our agile development process?
Right, creating the Kafka topics, letting the people writing the consumers know what are in those topics, and then migrating your Cassandra schemas to stay agile during the development time.
So the way we are processing, as I said, as we're incrementally building the platform, we look at one focus area or functional area at a time. So from a Kafka perspective, we didn't really find too much of time that we need to really spend on it. Once we define our structure of how you want to create the topics, how many of them, and how do you want to partition it, right, to spread across our Kafka cluster, that's pretty much it. And then the consumers of the data and the producer of the data is contained within the platform itself, right? So our consumer groups are set up appropriately in our microservices on the consumption side, and they would simply go ahead with whatever parallelism you need to read the data from. What we have not yet figured out is when we use Kafka as our distribution channel for the rest of the other enterprise organizations to come consume it, what is the best model for that? We looked at, there is a mirroring capability available in Kafka. So let's say there are two different Kafka clusters. Can you mirror data across? I think one of the feedback that we got from, we've been working with Confluent also on that, is no, don't do that. Is it easier to write a custom service which would be pulling data from it and then publish to the other cluster? That's an option. But so that's something that as a distribution channel, we have not got to it, but we'll have to address that at the time.
A question.
Yes, sir.
When you said that your write case was, your use case was very write heavy.
Yeah,
Sorry.
Can you speak up, please?
Yeah.
Very difficult to hear.
Your use case was very write heavy. That's what you said somewhere in your slides.
Mm-hmm.
I wanted to find out that was there a need to update any of those data, or is it always like add things to the existing data?
No, we do have inserts and updates. What we don't have is deletes.
Okay.
So being a data platform for reporting, operational reporting, we have constant data that we ingest. And we generally either insert because it's new data, or we do an update. So when we denormalize, we looked at what are the different options that we need to look at. Sets as one of the collection columns fit some use cases, maps fit some use cases. We try to stay away from frozen columns because updating frozen columns is a very tedious job, right? So that's pretty much it.
So you handle most of the stuff using basic data types to handle the complexity associated with updates.
Yeah.
You had a question.
Okay, the question is, have you experienced a data loss
So in
Kafka?
Kafka or in Cassandra? In Kafka. Not really. I think Kafka served us, I mean, this is not the first time you're using Kafka in our platform. We've had experience using Kafka in some other programs as well. So data loss as such, I don't think we've done that. We have other issues with Kafka, but not data loss.
So I mean, across Capital One, there are multiple Kafka clusters. For this data platform, we have a dedicated cluster that we have created, and we are using it for data ingestion as well as data distribution. And so as we're incrementally building the entire platform, we started with a 6-node cluster, and then we're probably going to add to that if need be.
What do you right over here? What do you plan on using for reporting tools to distribute the data out?
Yeah, so we actually have Tableau that we use extensively in Capital One. So our data model, like what Javed mentioned earlier, you had raw data and you have processed data. So processed data, when we process it finally, Tableau server is going to come and pick up that view from Cassandra.
You said that it was one of the key problem statement was to move from the batch world, both from the business organization perspective. But could you shed some light on from an operations monitoring perspective? Because operations also would be very much involved in monitoring and instrumentation. So the question is, what was the level of instrumentation that you had to do, and how did you set up your operational escalations to make sure everything is running?
Yeah, so we are still working on it. As I mentioned, as one of the challenges that we have is operational support. It's adjusting to the new technology stack. Exactly. So see, the entire DevOps-based model, we have been working in a more traditional operational support. So you do dev, QA, you hand it over through MOPs and whatnot, and then you go to a deployment and operationally support it. So we're changing that shift over to more a DevOps-based kind of model. So there's an adjustment there. And also it's no more you do develop and you throw it over the wall kind of a philosophy anymore, right? We are more tightly integrated from a dev perspective also. And the way we want to solve this problem is if we ourselves have to operationally support it, how do we do it? And then there are tools like, Mesos Marathon help there, Ops Center for data stacks is a good help. And then we also have used Splunk to carry some of the logs over we can do very close monitoring of how the system is behaving more proactively than reactively. So if you really look at it, the Go pipeline is more the internals of one microservice, right? So it's a one process really, So we not necessarily be able to really monitor within a Go microservice how the plugins are behaving. So, but as Mukram has mentioned, we bootstrap the service, right? And we deploy the service through a Docker container. And then, whatever the behavior of each of the plugins is monitored through through logs. And if there is anything that we see, any weird behavior on any of the plugins, we will catch through our proactive monitoring of that data. I think you have a question.
In regard to the Go technology, you had developed, you said 100% everything in-house. Did you use Sarama or any other open source projects to read from Kafka, or did you kind of?
We are actually using Shopify Sarama for Kafka, but that is not the actual framework that we have built. Oh. And I said there's a plugin that actually would go and produce or consume from a Kafka topic. That plugin would actually use Sarama. But the plugin internally will be run through a runner and a builder, and we have that platform itself. That's 100% in Go, not using any external libraries.
Okay.
Yeah, so we definitely leveraged Sarama's Sarama's library.
So continuing in the same path, right? So if you want to actually connect to an Oracle database, we would definitely use some Oracle driver out there to connect and build a plugin on top of that.
I get it. Thank you.
You had a question.
Well, okay, awesome question. So the two things that we have done. The question is, how long did it took us to take it from end to end into a production? We started working with a POC. It took us about 3 weeks to build the entire POC with 2 operational reports on it. on AWS with about 3 resources. I consider myself half, so 2.5 resources total, right? And then I think we spent, so right now we are in a pilot production mode. We have stood up this entire cluster on AWS within 3 to 4 months. And what the target is, as we are incrementally building the platform, we didn't want to necessarily come up with a bunch of business requirements and address it, but rather incrementally build our platform. So only one of the operational reports is what we have implemented on this platform so far.
So we've just been told that we're out of time. Probably we can take that question offline. Okay. So thank you so much. Thank you so much for coming and listening to us.
Thank you.